Hello and welcome to the Guide of Understanding Light Amplification by Stimulated Emission of Radiation, or better known as laser. There are tons of online information regarding laser physics, from very basic to deep scientific descriptions. However, from my experience working with students, but also with sales, marketing, and other non-scientific functions in companies involved in photonics, there is a need for an easy-to-follow, condensed, and concise guide to the fundamentals of lasers. This guide is almost exclusively on graphical and animation formats, and it is limited to the necessary details needed to understand the phenomena. It is supposed to be the first building block of the road towards a deeper understanding of optical fiber amplifiers and lasers, which are probably the most exciting applications employing laser effect. The first part of this guide is dedicated to the phenomena of photon absorption and emission, which is the foundation of laser physics. We assume the viewer to have some basic knowledge of physics. This includes: what is an atom, an electron, a photon? Also, it helps to be familiar with the notions like energy and wavelength. Nevertheless, for viewers' convenience, I have added links to corresponding Wikipedia pages for these notions. This presentation starts with a very brief description of the atom, then covers various photon absorption and emission mechanisms. Then we will cover various energy level systems, and also if and how these systems may be used to amplify the light. This is a very simplified drawing of an atom. Around the atomic nucleus there are a number of orbits characterized by a certain energy level. The further the level from the nucleus, the higher the energy level. The number of energy levels of these orbits vary from atom type to atom type. Each orbit can accommodate a certain number of electrons, but for simplification, during this presentation we will show only one electron on an orbit. Another important rule to remember is that electrons, if left free, will always try to populate the orbit with the lowest energy level up to the maximum number of electrons allowed for that orbit. In the following slides we will see how electrons can migrate from one orbit to another. The first situation is presented here, where we have an electron orbiting the nucleus on energy level E0. This level is usually named ground level. Let's assume there is a second energy level, E1, which is not occupied by an electron. To move the electron from E0 to E1, the electron needs to receive an energy equal with the difference E1 minus E0. This energy might come from various sources, but for the purpose of this presentation, we consider the case of transferring energy from a photon. So, let's assume that a photon having the energy equal to E1 minus E0 is colliding with the electron. The electron absorbs the photon energy. Having now energy E1, the electron will jump to the upper orbit E1. The photon disappears, its energy being absorbed by the electron. After transition to an upper level, the electron is known to be on excited state. In the vast majority of cases, due to causes that go beyond the scope of this presentation, the orbits, or energy levels, are in fact bands of energy. These are formed by a number of distinct but very dense levels. So, in practice, the electron on band E0 can sit on any level of this band. Also, when arriving on band E1, it can sit on any level of band E1. As a result, there are small variations of the energy difference E1 minus E0, and thus, the electron can absorb photons within a range of wavelengths, named absorption band. It is important to remember that the photon will be absorbed by the electron only if the photon energy is within the absorption band. If not, the photon will travel undisturbed by the electron. Another important fact to be noticed is that some atoms might have several unoccupied energy bands above E0. In that case, the electron is able to absorb photons corresponding to each absorption bands. Moreover, some energy bands might be very broad. So electrons can absorb photons having energy corresponding to various energy sublevels in that broad band. In some atoms, there could exist two unoccupied energy levels E1 and E2 equally spaced above E0. Let's assume the electron absorbs a photon with energy E1 minus E0, reaching the excited state on level E1. While being on the excited state, the electron may be hit by another photon from the same source with the same energy, absorbs it and then transition to level E2. This second transition is named excited state absorption. It is important to understand that electrons stay on the excited level only a certain time before they spontaneously decay to the ground level. The time interval is named energy level lifetime. There are two distinct situations. 1. If the energy level lifetime is very short, let's say microseconds or low, the energy level is considered as non-stable. 2. If the energy level lifetime is relatively long, let's say in the milliseconds range, the energy level is considered as metastable. As we will see in the following slides, this distinction is very important in the lasing mechanism. By contrast, the ground level E0, where the electron can stay an undefined amount of time, it is considered a stable level. As it has been mentioned at the beginning of this presentation, if left alone, the electrons will naturally tend to move to the lowest energy level that has an empty location for the electron. Considering that the electron has absorbed a photon and jumped from level E0 to level E1, after a while it will transit back to level E0. During this transition, the electron will lose an energy equal to the difference between E1 and E0. There are two forms of this lost energy. The first one is vibration of the material structure, or phonon. In practice, this is heat transferred to the material. The second form of energy that can be produced is a photon with energy E1 minus E0. Which form of energy is generated depends on atom type and its surrounding environment. This subject will be discussed in more detail in another presentation. Let's assume that between the excited level and ground level there are several intermediate energy levels. The electron will decay on multiple steps towards the lower empty energy level. For each intermediate transition, the energy lost by the electron will be converted to phonons, or to photons, depending on the atom type. In this example, the first and the third transition generates phonons, and the second transition generates a photon. Now, let's assume that a photon having the energy equal to E1 minus E0 approaches an atom having the electron on a upper metastable level. Also, let's assume that the electron transition from E1 to E0 will generate a photon. Because the lifetime on the metastable level is relatively long, there is a high probability that the photon will hit the electron before the electron will spontaneously decay. What is happening? Two things. 1. The electron will be kicked off from the metastable level and will decay to the ground level, generating a photon with the energy E1 minus E0. This photon will have the same energy, phase, direction and sense of propagation as the original photon. 2. The original photon will preserve his energy, direction and sense of propagation. As a result, after collision, there will exist two identical photons propagating together. This is the core phenomenon of the laser physics, and it is known as stimulated emission. Just a note on a particular case. What happens when the electron sits on a metastable level and there is another upper energy level equally spaced? If a photon having the corresponding energy is hitting that electron, any of the two effects may occur. Either excited state absorption or stimulated emission. The probability split might be different than 50%, so from case to case, that is, atom type to atom type, the corresponding emission and absorption bands might not overlap completely. Until now, we have identified two important conditions necessary in order to generate photons. The first is for the atom to have a metastable upper level. The second one is for the electron transition from the metastable level to the ground level to generate a photon, not a phonon. In the following slides we will analyze several energy level structures to see which can be used to increase the number of photons, that is actually the phenomenon of light amplification. We have here the simplest structure having only two energy levels, ground level E0, a metastable level E1. Having only two levels, the only interaction possible is with a photon having the energy E1 minus E0. So, let's consider that the first photon is approaching the atom and collide with the electron on the ground level. The photon is absorbed, and the electron will jump to the metastable level E1. Now, let's assume that the second photon is approaching the atom and interacts with the photon on the metastable level before the spontaneous decay. As a result, the electron will decay to the ground level emitting a second photon, and the incident photon will continue its path. This is the stimulated emission. Let's compare the original state at T0 with the final state at T1. At T0 we have two photons and the electron at the ground level. At T1, we have the same two photons and the electron on the ground level. We can conclude that ideally, there is no amplification, we preserve the number of photons. In addition, for a certain bulk material, there are actually many mechanisms that reduce the number of photons at T1. Some electrons from the metastable level will spontaneously decay before encountering a photon. Also, some photons will simply be lost being absorbed by the material impurities, or scattered out of the material without hitting an atom. So, in practice, we will have attenuation and not amplification. In conclusion, the two-level system is not suitable for light amplification. Let's now assume a more complex system having four levels, E0, E1, E2 and E3. Let's also consider the levels E1 and E3 are non-stable, so the electron decay will generate phonons. The level E2 is metastable, so the electron decay from E2 will generate a photon. Our first observation is that this system, having various energy levels, can interact with several photon wavelengths. Now, let's consider that a photon with energy E3 minus E0 is approaching the atom and collide with the electron in the ground state. As expected, the electron will absorb the photon and will jump to the level E3. But level E3 is not stable, so the electron will rapidly decay, not generating a photon, to the level E2. E2 is a metastable level, so the electron will spend some significant time there. If nothing happens, after a while, the electron will spontaneously decay to the non-stable level E1, then quickly back to the ground level. Because E2 is metastable and E1 is non-stable, in bulk material flooded by photons with energy E3 minus E0, at any moment in time there will be more electrons sitting on level E2 than sitting on E1. This situation is named inversion, because the population of atoms having a higher level occupied is higher than the number of atoms having a lower level occupied. The inversion can occur only under presence of incident photons that pumps the electrons from the ground level to E3 and then decay rapidly to E2. Inversion is another fundamental phenomenon for the light amplification, and we'll see why in the next slide. So, as we saw, the incident photon, colored in green, will populate the metastable level E2. Now, let's assume that another photon, colored in red, having the energy E2 minus E1, is approaching the atom and interacts with the electron sitting on the metastable level E2. Because the photon energy corresponds to the energy gap between E2 and E1, the stimulated emission occurs. The electron will decay to level E1, emitting another photon with energy E2 minus E1, while the original photon will continue to its original path. Then, of course, the electron will immediately decay to the ground level. If we look at the original system state, T0, we see that we have one green and one red photon, and the electron on the ground level. The final state at T1 shows two red photons, and the electron on the ground state. So, we can see that this system is able to double the number of red photons, that is, light amplification. Of course, this is at the expense of the green photon, but this is absolutely normal. Any amplifier has to consume power in order to function. The key element that makes this amplification to work is for the incident red photon to have a higher probability to interact with the electron on level E2, where stimulated emission occurs, and not on E1, where absorption would happen. As we discussed earlier, this four-level system ensured that the population on level 2 is higher than the population on level 1, so, for the red photons, the probability of stimulated emission is higher than probability of absorption. Of course, in practice, there will be various loss mechanisms that will reduce the gain. We will discuss them in another presentation, but the important thing is that such four-level system can amplify the light. The four-level system is not the only system that can amplify the light. Let's consider a three-level system. Here, the level E1 is metastable, while E2 is non-stable. The green photons will stimulate the electrons from the ground level to level E2, from where they will rapidly decay to metastable level E1. The red photons, having the energy E1 minus E0, will be amplified by stimulated emissions from the electrons decay from E1 to E0. But not all electrons from ground level will absorb green photons, some will absorb red photons. This is possible because the red photon's energy is equal to the energy gap between E0 and E1. But the higher the inversion level, the lower population of electrons on the ground level. So, less red photons will be absorbed on the ground level. However, the gain of this system will be decreased by this phenomenon. Let's consider now another version of three-level system. Here, the metastable level is E2, while E1 is non-stable. The green photons will populate level E2, where the red photons will generate more red photons through stimulated emission. Because the population on level E1 will always be negligible, the absorption probability for red photons is virtually zero. However, the green photons can also interact with the electrons on E2. That reduces the probability for the red photons to produce stimulated emission. This will reduce the gain efficiency of this system. In conclusion, while three-level systems can be used to amplify photons, their efficiency is lower than four-level system. Now, let's take a look how these phenomena happen in a bulk material. The atoms involved in absorption and stimulated emission, named active atoms, are marked with circles. Let's assume these atoms have a four-level system. The light blue circles represents the atoms having the electron on level E0, dark blue have the electron on non-stable level E1, red have the electron on metastable level E2, and violet have the electron on non-stable level E3. If this material is flooded by photons having energy equal to E3 minus E0, represented here by the green lines, some of the active atoms will be hit by these photons. Their electrons will absorb the green photons and will jump to level E3. For that, they will rapidly decay to metastable level E2. Now, let's consider that a photon having energy equal to E2 minus E1 is entering the material and collide with an excited atom. The stimulated emission occurs, and a second photon is generated. This phenomenon might happen again if any of the generated photons encounter another excited atom. Depending on the number of excited atoms encountered from one input red photon, we might obtain at the output a larger number of red photons. Similar process will happen for each red photon entering the material. Some of them will not encounter any excited atoms and will leave the material without amplification. However, on average, the output will exhibit a much larger number of red photons compared with the input. But we should not forget that some excited atoms will not be hit by any red photon. In that situation, the electron from the metastable level will spontaneously decay to the ground level and will emit a red photon. This red photon travels through the material and could collide with another excited atom. In that case, the stimulated emission will happen and two red photons are generated. The process may repeat until the photons will exit the material. This phenomenon is named amplified spontaneous emission, or ASE, and can happen anywhere in the material. It is very important to notice that red photons generated by the spontaneous emission will propagate in any direction, while the red photons generated by stimulated emission will always propagate synchronously with the incident red photon. They will have the same direction, sense and phase. To be noticed that the signal amplification and ASE will happen simultaneously in a bulk material. So, if the material is pumped, the signal photons coming from outside will be amplified by some of the excited atoms. The rest of the excited atoms will emit spontaneously photons which will create ASE. We reached the end of this first part of the lecture on understanding lasers. In part 2 we will describe the three main applications of the light amplification. These are optical signal amplifier, ASE source, laser. Thank you for your attention. Please do not hesitate to comment on this presentation if you have any observations or suggestions. Our website is www.optoilsoft.com.